Hello, welcome to everyone in this video. This is the lecture number 1 on statistical mechanics. In this video, I want to discuss the micro and macrostate, ensemble, and ergodic hypothesis and phase space. Right? You can see this is the syllabus of semester 5 of Calcutta University Physics Honors. Right? Physics Honors. So this is the syllabus statistical part, and you can see this is classical statistical mechanics, system of identical particle, then Bose-Einstein statistics, then radiation, classical and quantum aspect, and finally Fermi-Dirac statistics. In this video, I want to discuss this portion, that is the macrostate and the microstate, then elementary concept of ensemble, then ergodic hypothesis, statement only, and phase space. So this part will be covered in this lecture, and the upcoming lecture consists the following syllabus, right? So let's start. First, we need to understand what is the statistical mechanics. Consider any thermodynamics variable. If you want to find out the measurement of any thermodynamic variable, that is the find the any thermodynamic variable, you wants to find out any thermodynamic variables, then you have different methods. You have already learned the about different thermodynamic method. If you want to find out any thermodynamic variable, you have two broad method, that is microscopically and macroscopically. Microscopically means constitutional part, macroscopic means all about the properties. So you can see macroscopic and the micro microscopic, right? Macroscopic and microscopic. Macroscopic mean all over property. Macroscopic mean all over property means you have a container. Suppose you have a container, so you can see its pressure, its volume, its temperature, its density. These all are the macroscopic property, because it's the pressure is the total property of this container, temperature is the total property of the container, volume is also the all over the total property of this container. So these are the macroscopic, right? So macroscopic means all over the property, and microscopic means if you find out the individual particles property. Suppose you have these particles, ideal gas or real gas, you know its momentum, you know its velocity, you know its mass, right? So these are the individual particles property. So this is the individual particles properties, right? Individual particle properties. This is the microscopic. In the macroscopic, the study is the thermodynamics. We already learned thermodynamic. So by this thermodynamic, you can find out the thermodynamic variable. No problem. This is the macroscopic property, all about the property. In microscopic property, you have two methods. One is kinetic theory of gas, KTG, kinetic theory of gas. You already know about the kinetic theory gas, where we consider individual particles property, right? You know, consider individual particles property, you know, property, right? Here you know individual particle property, and finally you find out the pressure, energy, etc. in terms of their constitution. So what happened in thermodynamics, you measure all over the property, whole property. In kinetic theory, you measure the individual properties, particles property. So you know in a container there is a 10 to the power 23 orders of particles. So you have 20 to the power 23 numbers of equation to solve this parameter. So actually we want to deal with the individual particles such that we get the actual information of the system. Actually, in thermodynamics, we got the overall picture of the system, but we wants to find out the actual property within the system actually happen. That's why we take the microscopic measurement, and from that we consider the kinetic theory of gas, where we calculate these 10 to the 23 numbers of equation to solve this. We solve this 10 to the 23 numbers of equation to get the properties of individual particle. But this is a kanji, and this is a very difficult to solve this number of equation. So that's why the effective of these two combination, that is first choice is to find out the individual's particles property, and second choice to reduce the numbers of equation is the statistical mechanics, which helps to us statistical mechanics. This actually helps us to reduce the numbers of equation and to find out the individual's particles property. So these are our benefits. Here we can reduce the number of equation, and here we got individual particles properties, right? So these are benefits of these two drawback of thermodynamics and kinetic theory of gas. Finally, we use the statistical mechanics. In the population count or etc etc, and sometimes says that in this region the 25% illiterate are there. They does not individually count in this region in the population count of this India. Suppose if you consider these Indias, right? So you just then think about this India. Okay, I can you just so if you consider the population density like here, they does not take the individuals peoples to count their literacy or etc etc. They statistically says that in this region these are the this person of illiterates are there. Okay, so this is the statistical mechanics, where actually take some samples like there and conclude the all over this region. So this is the method by which we get the individual's particles properties with the minimum number of equation or the minimum numbers of variables. Okay, that's the motto of the statistical mechanics. I think clear about the statistical mechanics. All are wants to find out the thermodynamics variable, macroscopic property. Macroscopically considering, we get thermodynamics, microscopically kinetic theory gas, and the statistical mechanics. Clear? Statistical mechanics have two parts. If you find out statistical mechanics, it's two parts. Number one is the classical statistical mechanics and the quantum statistical mechanics. In classical statistical mechanics, number one, energy is continuous. Energy absorbed or is emitted is continuous. But in quantum statistical mechanics, energy absorbed or emitted is quantized. That's why it's quantum. So energy absorbed or absorbed B. I don't sorry B. Absorbed or emitted is quantized. That's the basic difference. And here the in classical statistical mechanics, the particles are distinguishable. Particles are distinguishable, right? Distinguishable. And in the quantum mechanics, particles are indistinguishable. Particles are indistinguishable. So in the question they does not mention is this quantum statistical mechanics or the classical statistical mechanics. By the language of this question you need to know, or you need to classify whether this is a statistical quantum statistical mechanics or classical statistical mechanics, right? So you need to know this, the property of the classical statistical mechanics and the quantum statistical mechanics. I think clear about these two properties. Okay, in classical statistical mechanics there is a Maxwell Boltzmann statistics or distribution. Maxwell Boltzmann distribution or statistics. Maxwell Boltzmann statistics is the category of the classical statistical mechanics. Whereas in quantum statistical mechanics there is two distribution: Bose-Einstein statistics, Bose-Einstein statistics, Einstein statistics, and number two is Fermi-Dirac statistics, right? Fermi-Dirac statistic. Okay, statistics. In Maxwell Boltzmann statistics, no consideration of spin, no consideration of spin. Okay, here we do not consider any spin. In Bose-Einstein statistics, the spin is the integral multiple, full integral multiple. So this is the spin is integral multiple, like H cross 2H cross etc. Or H cross, no problem, H cross 2H cross 3H cross and so on. And here in Fermi-Dirac, spin is odd half integral. Spin is odd multiple of half integral, like H cross by 2, 3H cross by 2, 5H cross by 2, etc. Okay, this is the spin consideration. In classical there is no spin consideration. In Bose-Einstein there is a full multiple of integer multiple, and this is the odd half multiple. Okay, number two property is the within a state of the, in case of Maxwell Boltzmann, there is no restriction of the number of particles. No restriction of number of particle in a cell. Here also in Bose-Einstein, no restriction of number of particle in a cell. There is no restriction also. But in Fermi-Dirac distribution, they follow the Pauli exclusive principle, and here they follow the Pauli exclusive principle. Restriction obey by Pauli exclusion principle. Okay, I think you understand the statistical mechanics category: classical statistical mechanics, quantum statistical mechanics. In classical, Maxwell Boltzmann statistics, and in quantum, Bose-Einstein and Fermi-Dirac. In classical, energy is continuous. In quantum, energy is quantized. In classical, particle are distinguishable. In quantum, particle are indistinguishable. In classical, there is only Maxwell-Boltzmann statistic. In quantum, there is Bose-Einstein and Fermi-Dirac statistic. Maxwell-Boltzmann statistics, there is no spin. In Bose-Einstein, spin as integer multiple, and in Fermi-Dirac, there is odd multiple of half integral. And in the Exclusion principle only obey the Fermi-Dirac, they obey the Pauli exclusion principle, and these two are not obey the Pauli exclusion principle. I think you understand the all about the statistical mechanics. If there is any doubt, you must comment in the comment box. Now goes to the two parameter, that is the microstate and the macrostate. Macrostate and the microstate. Now just before discuss, there is a system. This is a system. Suppose this is a any system. In this system, you can say its volume, its temperature, its pressure. All these are the macrostate, because you obtain this in the all over the property macrostate. Okay, but in this position, in this particle, individuals particle, you get momentum, you get velocity, you get mass, you get linear momentum, the angular momentum, and orientation, etc, etc. So this all about the property of individuals particle. This is the microstate. This is the microstates. Okay, so I think clear. Microstate and macrostate. Macrostate is the all over property, microstate is the individual's property. You can see this definition like that. The term that describe the macroscopic property of a system, the most commonly measured microscopic property: pressure, temperature, volume, density, Hamiltonian. All over the property, total property of the system is the macrostate, and individuals particles property are the microstate, that is the level of atomic or molecular level constitutions property is known as the microstate. Clear? Microstate and the microstate. We want to deal with some example like that. You consider three coin examples. Examples. Number one, consider three coin. Consider three coins, right? You consider three coin. So three coins, number of possible state for three coins, you know, 2 to the power 3, so that is 8 number of possible state. What are these number of possible state? All three are head. You know to write these things. 4h, then for head, sorry, h means head, and then for tail there is some mismatch with the connecting. Okay, I just try to write with using mouse. So head, and this is the tail, because this pen is not working at this moment, that's why we try to write with the help of mouse. So head, tail, this is very problematic position, but I just try. This communication is not help us to draw this curve. Okay, I please try to understand, because this is technical fault. And this is head, tail, head, tail, head, tail, head, tail. Okay, these are the microstate. These are the microstate. Oh, this written is very problematic. Microstate. Okay, problem solved. These 8 are the microstate. Okay, and you can see in macrostate, this is a macrostate, 3 head and 2 head 1 tail, that is this 2 head 1 tail, 2 head 1 tail, these three are 2 head 1 tail, and this is 2 tail 1 head, 1 head 2 tail, and this is 3 tail. Clear? So this actually there is 4 macrostate. I think clear. Macrostate are like that: 3 head, 2 head, 1 tail, 1 head, 2 tail, 3 tail. These are four. So macrostate is 4 and microstate is 8 here. I think clear. Next example goes to the next example. Suppose there are 5 particles. Consider 5 particles. Consider 5 particles. Classical 5 particles. That's mean classical means distinguishable. Distinguishable, right? There are distinguishable 5 particle. Total energy, where total energy is 4E is given 4 epsilon. But there are energy available. The energy availables are like that. 3 energy availables, 0, epsilon and 2 epsilon. Energy levels, 3 energy levels are available. 5 particles, total energy 4 epsilon. What are the, this is one macrostate. This is the macrostate condition. Macrostate condition. Okay. This is the macrostate condition. I just remember you that within one macrostate there are large number of microstates. I write down here within one macrostate there are many microstate present. Microstate present, right? Within one macrostate there is various microstate are present. Okay, so if you this is a macrostate, what are the microstate in this condition? There are 3 energy levels. This is 0, this is epsilon, this is 4 epsilon. Sorry, 2 epsilon. Now if you want to obtain 4 epsilon energy within the 5 particle, you can see if you take 2 particle into epsilon, the energy obtained 4 epsilon, so others 3 within 0 level. So total energy is 5 epsilon, no problem. If you consider another combination like that, suppose 1 is here, 2 and 2 is here, so 2 and 2 4, so others 2 must be here. So this is another microstate. Suppose this 4 lying on that one and number 1 is here. I think these 3 are the possible microstates. So these 3 are the possible microstate. So within one macrostate there are 3 microstates. Clear? I want to give you another example. Example number 3. Consider 4 distinguishable particles. Since these are the distinguishable, consider these are A, B, C and D. These are the particle identity within 2 boxes, A and B, capital A and capital B. So within these 2 boxes you need to place the 4 distinguishable particle A, B, C and D. So what are the number of microstate? What are the number of macrostate? Okay. Suppose macrostate. Suppose the macrostate, you have 2 box. This is A box, this is B box. Okay. And this particle, 4 particle like that, A, B, C, D. You need to place on this 4 particle within these 2 box. Okay. Suppose within A box there is 0 and within B box there is 4 number of particles. So arrangement will be like that. Within A, within B there is no, and there is A, B, C, D. So the microstate will be 1. In case of 1 3, within A there is 1. So if you place here A, there will be B C D. If you place B, there will be C D A. If we place C, there will be D A B. If you placed here D, this is A B C. So these are the 4. Clear? Now if you 2 and 2, if you place there is AB, so there is CD. If you place AC, there is BD. If you place AD, there is BC. Okay. Then if you place here BC, so there is AD. If you place here BD, then AC. If you place here CD, you placed AB. Okay. So these are the 6 microstates. Now if you just write down here macro and micro. I think clear. If you place 3 in box A and 1 in box B, so that's reverse one like that. So these 4 are, so this is A B C D, and these are the within B configuration and within A configuration. So rest 3, so there are also 4, and there will be 4 0, so that's reverse one there, and there is A B C D. This is 1. So finally 1 4 5 1 4 5 5 5 10 and 6 16. So number of microscope, total number of microscope, if you find out the total number of microscope. Okay, again the problem arises. I just mean this total microstate. Total microstate. What will be the total microstate? Try to solve this problem. Okay, problem solved. Total microstate is 10, 10 is 16. And macrostate, total macrostate. What will be the total macrostate? Is 1, 2, 3, 4, 5. Clear? So I think clear about the concept of microstate and macrostate of a particular case. Okay. Now the next point is the ensemble. Okay, this is an important concept. You need to know about the ensemble. Actually, ensemble is the mathematical tool. This is the mathematical tools to offset, to study the statistical mechanics. This is the mathematical tool. This is actually the mental copies of the microstate. This is the mental copies of original system that are macroscopically identical but microscopically different. This is the main things. You can see here in the example of previous example, here you can see within that this is the one macrostate, but there are 6 microstate. So these are the ensemble of this macrostate. So one single macrostate, there are various microstate. This is the ensemble. One single macrostate, there are various microstate. These various microstate known as the ensemble. The macroscopically identical but microscopically different. This is the main things of the ensemble. Okay. So what are the number of ensemble within ensemble, number of state within ensemble? If you can say the number of state within an ensemble, this is nothing but the in number of microstate of this macrostate. So within that macrostate, number of microstate is nothing but the number of state within this ensemble. Okay, there are different type of ensemble available. Okay, different type of ensemble available. Different ensemble. This ensemble are classified as that. First one is the micro canonical ensemble. Micro canonical ensemble. First one is the micro canonical ensemble. Within the micro canonical ensemble, the constant are the number of particle, volume, and the energy. These are the constant in the micro canonical ensemble. So number of particle constant, that is, this is closed. This implies closed. And energy also constant, that means it's isolated. So in thermodynamics you can correlate in thermodynamics like the closed system. Closed system. In closed system, you know dn equals to 0. No number of particle are outgoing to system to surroundings, right? And the energy transmission also provident. So the E also 0. This is called micro canonical ensemble, where the number of particle, volume, and energy, these are the constant. Okay, this is called isolated or closed system. No, this is isolated, not closed system. Isolated system. Number of particle number of particle not transmitted, and energy also not transmitted or transfer with the surroundings. Next one is the canonical ensemble. Number 2 is canonical ensemble. Number 2 is canonical ensembles. Okay, within canonical ensemble, the constant are n, v, and t. Since n is constant, so this is closed. Temperature is constant, this is isothermal. Isothermal means the system is temperature temperature is constant, energy can flow, but temperature is constant. So dn equals to 0, but de not equals to 0. This is closed system. You compare with this thermoflux. Within thermoflux, this is isolated system. Within a cup of tea, you just close by the plate. You can consider this is a closed system. And number 3 is the grand canonical ensemble. Grand canonical ensemble. Actually, we need to elaborate these things in upcoming lectures. At this moment, we just know about the types of ensemble. Here, this chemical potential, volume, and the temperature are constant. Mu is the chemical potential. Okay, T is the temperature. Here, this is the open system. Here, the chemical potential is constant, so dN not equal to constant, dN not equal to 0, and d not equal to 0. I think clear. So this is like a cup of tea without covering this. So mass also exchange and energy also exchange. So in microcanonical, mass and energy does not exchange, just like isolated system. In canonical, energy can exchange but mass does not exchange, just like a closed system. In grand canonical ensemble, energy and mass both are exchanged with the surrounding, just like a open system. You remember this constant. In microcanonical ensemble, the number of particle, volume, energy are constant. In canonical ensemble, number of particle, volume, temperature are constant. In grand canonical ensemble, chemical potential, volume, and the temperature are the constant of the system. In general, canonical ensemble are preferable, but why? We will discuss in the canonical ensemble chapter. In general, prefer canonical ensemble. Okay, and remember, for any type of ensemble, you got the same result using any type of ensemble. You got same result. This is the important of this ensemble theorem or ensemble use, that is within using any type of ensemble you got the same result. Okay, so I think clear about the ensemble. Ensemble is nothing but the number of microstate within a macrostate. This is the different type of ensemble: microcanonical, canonical, grand canonical. Microcanonical means isolated system, canonical means closed system, grand canonical means open system. I think you remember these things. Okay. Now go to the theorem, Ergodic theorem. This is also known as theorem, that is the probability a priori. A priori probability. This is also known as the probable. This is also known as the postulate of, okay, sorry, of equal a priori probability. It says that within a macrostate, any type of macrostate, I just write down this macrostate like that. For example, 2 in the box AB example. Take this before example, this one. I want to refer this example. Okay, I want to refer this example. In this example, you can say this is the macrostate and this is the microstate. So within this macrostate, there are 6 microstate. So the probability to getting these 6 microstate are equally probable. That's the hypothesis. Okay, so that is the hypothesis which says that these six microstates are equally probable to occur. This is the probability theorem. You can say this is the probability. Okay, so in definition you can write on that the system is considered to be in equilibrium if it samples all the microstates with equal a priori probability. Equal a priori probability মধ্যে সবগুলো থাকবে, জাস্ট probability equal হবে, ঠিক আছে। In the different language you can say that is the time and ensemble average of a thermodynamic quantity are the same. Okay, this is the Ergodic hypothesis. So I think clear this hypothesis. This is the equal a priori of the probability. Just the probability of getting any microstate of a macrostate are equally probable. That's it. Now comes into the point, that is the phase space. What do you mean by phase space? This is nothing but the momentum position coordinate. Momentum position coordinate. Momentum position coordinate means px, or you can see L theta. Angular momentum, angular position, angular linear momentum, linear position. This phase space mainly two category. Phase space have two category. Number one, mu space. This is for single particle. This is for single particle, and this is gamma space. This is for n particle. Okay, that's the difference. Mu space for single particle, and this is for n particle, n greater than 1. Okay. There is momentum and position coordinate. So if you got degree of freedom in free space, you already obtained degree of freedom. Degree of freedom. Degree of freedom in real space. Real space. Real space means x, y, z. In real space, degree of freedom consider as f. You know this f equal to dn minus k. dn minus k. Where d is the dimension. 1 dimension, 2 dimension, 3 dimension. Dimension. And n is the number of molecule. Number of molecules. Atoms, I think. Atomic, atom, not molecules. Number of atom. Diatomic, triatomic. And k is the constant. Okay. So you got this degree of freedom. After getting the degree of freedom in the space and the momentum also f, so you can see that is the dimension in mu space. In the mu space, the dimension will be 2f. Degree of freedom, that is the real space, and number of dimension in real space equal to the momentum, because if you three coordinate x, y, z, their corresponding momentum are px, py, pz. So there are 6 dimension in real space. So if you degree of freedom f, so their mu space dimension will be 2f, and dimension in gamma space, if you say dimension in gamma space, what will be the dimension of gamma space? If there is n number of particle, for single particle there is 2f, so n into 2f, this is the dimension of gamma space. Okay, take an example. Diatomic particle. Okay, take an example, diatomic particle. This is the 2. So degree of freedom f equals to dn minus k. So you can find out dimension in mu space. Mu space dimension in 3D. In 3D, that is 3 into n is 2 minus 1, that is 5. Okay. This is f, so you must multiply with 2, that is 10. In 2D, there is 2 into 2 minus 1, that is 4 minus 1, 3, that is 6. In 1D, that is 2. 1 into 2 minus 1, that is 1 into 2, that is 2. Clear? For 10 particle, if you want to find out gamma space, so just multiply this 10 with this one. So 3D, this will be 10 into 10, that is 100. For 100. For 2D, that is 10 into 6, that is 60. For 1D, that is 10 into 2, that is 20. These are the dimension in the gamma space. I think clear about the one. Now comes into the generalized form. This is very important part, generalized form. Consider in quantum mechanically, so in mu space we just know about mu space. Gamma space is nothing but the multiply the number of particles. In mu space, You can see there is two things, that is the position and the momentum. And you know from the uncertainty principle this value is nearly to h. So in this space px, py, pz, the small volume will be, that is delta y, delta, this is px, delta py will be h, and delta z, delta pz will be h. So the small volume will be h, that is h cube. This is the small volume in space, in the mu space, small volume. So small volume will be hq. I think there is no doubt about this information. Okay. In 3D, in 2D this is h square, in 1D this is h. I think clear about this thing. Now if you find the volume within mu space volume, so just integration d 3n q is the position, and 3n p, this is position, and this is momentum. Here this is position and this is momentum. If you consider the real space, 3-dimensional real space, so this will be d3q and d3p. So this is the real volume and d3p, and this volume is nothing but 4 pi p square dp, 4 pi d square dp. Okay, so this is the small u, and so finding the value of p, you will be get the, so number density, that is the because the volume of the unit is like that, and this is total volume, so number density means number will be v by hs cube 4 pi p square dp. So this is the number of the state, number of states. Okay, so because this is a unit volume, the volume of one state, one microstate, this is the volume of one microstate, so divided by this one. This is for 3-dimensional. If you consider 2-dimensional, this will be area, and this will be 2 pi r, that's r is not p dp, this area. So number of state will be area by h square 2 pi p dp, and 1 dimension this will be length, and this is length, cancel out, will be only dp. Okay, I think you clear about this one. This is 2 pi p and this is dp, this is the small area. Okay, and in case of this volume also, this is 4 pi r square is surface area. If you multiply this dp, you will be give this volume in the these two concentric sphere. This is sphere and this is circle, these two are different. I think clear. If there is any doubt, you must comment in the comment box. So today we will learn about, just revise at a glance, macrostate, microstate, then ensemble, and this hypothesis and phase space. We will learn about this one. Okay, now we want to just go through the previous year question actually asked in the University of Calcutta. First one say, plot the phase space trajectory of a particle falling freely under gravity. Suppose there is a particle which falling under gravity. This is ground. Okay. If you consider this is a, height h. Now at any moment at this position, this distance is x. So at this position, its its velocity v. So v square, so v square equal to u square plus 2g s. So u is here 0, so 0 plus 2g, and s is nothing but this distance, that is h minus x. Okay, so this is the v square. So if you change into phase space trajectory means momentum and the position. So momentum p equals to mv, so v equals to p by m. whole square equal to 2gh minus 2gx. So p square equals to 2gm square h minus 2gm square x. Just think, what is the diagram of this one? Suppose when x equals to h, when x equal to h, p equals to 0 at this moment, and equation also says at when x equals to h, p equals to 0 at this point. And if you increase the x, sorry, if you reduce this x, p will be increased. If you reduce this x, p will be increased. And when x is 0 at this position, p will be maximum, like that. So this will be the nature of this curve. Okay, this value will be like that, 2gm square h will be the maximum height. So I think clear about the trajectory of this curve. Phase space trajectory freely falling under gravity. Next question says state the postulate of equal a priori, which already we discussed, that is the hypothesis, that is the Ergodic hypothesis. We already discussed this hypothesis. That is, all microstates are equally probable within a macrostate. Next thing says for a single spinless non-relativistic particle of mass small m confined in a volume V in 3D having energy between E and E plus D. Write down the region per volume of the phase space. Okay. So we already just discussed phase space region where energy between, actually we write down in momentum space, momentum between P2 P plus dP. So this will be nothing but volume and 3pq, that is volume into 4 pi p square dp. So we need to convert p into energy. Okay, so you know energy equals to p square by 2m. So what will be the value? That is dE is nothing but 2p dE, sorry, 2p dP by 2m. So you just write down like that, 4 pi p into p dP. So p dP gives you m dE and p gives you root under 2me. So just substitute here, that is v 4 pi, p is root under 2me and it is m dE. So you will be get this one, that is 4 pi v root under 2me and 2me m into d. So this will be the energy between, this is the region per volume of this phase space. So this is the number of states within, actually number of state mean you need to find out divided by hq, but here this says particle confined a volume v, write down the accessible region. This is the volume, actually phase space, volume in phase space, this is the volume in phase space, sorry, volume in phase space, volume in phase space of energy E and E plus D. Okay. Next question says, by evaluating the volume of relevant region its phase space so that the number of its phase space, so that the number of microstate available to a rigid rotator, angular momentum less than m is like that. So rigid rotator, that's mean one coordinate is fixed. So here you consider two dimension. That's one thing you need to consider, two dimension. Now the volume will be integration to p Q and P. Okay. Here the angular, since this is a rigid rotator means angular, so you need to consider 2 theta and 2 L. So in theta the angular, that is the 2 pi. This is nothing but the 2 pi. Okay. I think you understand, that is 2 pi, and this is the maximum momentum N. So this is the, if you consider the actually whole square, that is integration of d theta is 2 pi and integration of dl is m, and there is a square, so this will be the whole square. Okay, so this is the area, because this is two dimension, the area in phase space. Phase space, this is the area in phase space, and you know in the phase space, small area in this phase space will be h square, h into h square. So you just divided this one, h square, you will be get the number of microstate. Number of microstate will be nothing but 2 pi m h square. So this is 2 pi m by h whole square. Simple, I think simple, right? Next question, what do a microstate and the macrostate represent a phase space of a statistical system describing n particle moving in 3 dimensions? That's already we discussed. This is the microstate. Microstate is nothing but integration d3n q d3n, actually write one integration p. This is the number of microstate within a macrostate. Within a macrostate. Okay. Next question. Assuming the entropy of a function of number of microstate will be this. So omega is the microstate, S is the entropy. So that the additive character of S, entropy is additive, and the multiplication character of omega, microstates are omega, necessarily this one. So S is says that is additive, and omega is multiplicative. You just think the mathematical tools which multiplication turns into addition, multiplication converted into addition in the logarithmic scale. If no, that is ln AB, that is multiplication turns into the addition ln A, ln B. So you just say that is ln omega 1 omega 2 can be written as ln omega 1 plus ln omega 2. So you can just write this is S1 plus S2, and this 2 will be total S. So you just conclude that is S must be proportional ln omega, such that we can conclude that is this multiplication can be written as the addition of like that. So I think clear about this one. If there is any doubt, you must comment in the comment box. So this is all about me, and this is my contact detail. You can connect me with this Telegram channel. And this is my YouTube channel details. Go to this channel, we get the physics related video, mathematics like this session. If you learn something from this session, share this video to your friends. Other yes, she also get sorry. When we found the video, subscribe the channel if you new in this channel. Those already subscribed, thanks for subscribing. Press the bell icon to get notification of our video. So take care. We'll meet you in the next video as soon as possible. Thank you.